تيست دابا كتسمع تيست دابا كتسمع
Test. Test.
C'est bien. Normalement, une demi-cravate intérieure.
Donc je peux pas, j'aurais pas besoin de me tenir au micro, Yak. Si.
Si, pour juste pour le.
Voilà ça. سي عمر تبارك الله عليك.
تيست
شويه ديال
تيست
لا كون هاني تكون هاني. شويه د l'arithmétique شويه التوبولوجي شويه ديال توبولوجي. كاين كور توبولوجي في بروميير اني ديك صح.
كاين توبولوجي كاين في بريبا.
كاين بريبا واي.
مي
كتبان. Non, je serais très. J'espère. Il n'y a pas de preuves, il y a beaucoup d'images, beaucoup de. Je vais commencer par définir les entiers 0, 1, 2, 3, 4.
Ouais, non.
Oui, mais c'est pas pour raconter une histoire.
Pour le muter, juste appuyer là.
Ok.
Et le démuter,
Ça marche. Test. Ça marche pas. Si tu veux, tu peux utiliser le même, les voitiers. Ou la... Non. Ok.
Tu peux le muter d'abord si tu veux.
Ouais.
Je peux le muter derrière.
Ouais.
Et je fais la même chose.
Test. Test.
Okay. Welcome back, everyone. Again, congratulations on your 2 days of intense for our exams. I hope you had the chance to relax. I hope you had the chance to have some food, talk to your friends. So the next part of our event is going to be a series of 2 conferences. So we're very lucky to have our 2 esteemed speakers, Professor Salim Tayou and Professor Ida Laraki, which is going to join me soon. So let me start by presenting Professor Salim Tayou. So you probably already saw the information we put out online, but Professor Salim Tayou is originally from Tangier. He did his preparatory classes in Tangier, so he started his first year in Tangier, and then went to Lycée Moulay Youssef at the MP Étoile in Lycée Moulay Youssef, after which he joined the very restricted club of Moroccans who joined l'École Normale Supérieure de Paris, or as many of us know it as ULM. After which he started his PhD in Université Paris Sud in pure mathematics. Without going into the detail, I'm sure he'll talk more about this in his presentation. Well, after his PhD and following many academic adventures in Canada and in the United States, Professor Tayou joined Harvard as in a 3-year fellowship, and he recently joined Dartmouth as an assistant professor. Professor Salim Tayou, we're very fortunate to have you here among us, and the floor is yours. Please, a round of applause for us.
Well, thank you very much for the very kind introduction. I'm very pleased to be here with you today. So I prepared my talk in English, but I also can switch to French. If there are any questions, or just please raise your hands and feel free to interrupt me. The title of my talk today is the topology and the arithmetic of algebraic varieties. So this is going to be a very panoramic talk about some of the topics I like thinking about, or I enjoy in my daily life as a researcher. And I would like to start very basic. So by redefining or maybe rethinking the numbers. When we think about numbers, namely the integers like 0, 1, 2, 3, so on and so forth, there is a step in which we conceptualize the fact that there is 2 oranges, 2 people, 2 of something, and the common thing between these things is the number 2. And so in some sense, like the non-negative integers are natural. This is like why in French or like in Arabic, we call them al-a'dad tabi'iyya, or les antinaturels. So they're naturals in some way. The set of extended integers, like when we introduce -1, -2, this requires a little bit of thinking. Like, is the number -2 is the number such that when you add it to 2, you get 0. Then the notion of rational numbers, when you write P over Q, this arises naturally when you want to subdivide, let's say, 3 oranges among 2 people, then each one will get 3 halves, right? Or 100 oranges over 3 people, well, each of them is going to get 33.33333, but in fact, it's not an integer. You cannot write it as minus something, like a number or like an integer. So it's like a genuinely new class of numbers. Now, the real numbers, you need something a little bit more. For example, square root of 2, like naturally, which appears just the length of a right angle triangle, like the hypotenuse. Well, you can construct it, but maybe you have already done the exercise where you showed that square root of 2, you cannot express it as P over Q, right? Has anyone ever done this exercise before? Like, prouver que racine de 2 n'est pas rationnelle? Raise your hands. Okay, those who have not raised their hands, do this exercise tonight. Prove that square root of 2, if you cannot write it as P over Q. Or maybe just from here until the end of the hour. So, and there are much more. They're like the number E, the number pi, and in general, if you've taken some class in topology or analysis, you've seen that there are many ways to construct the set R of real numbers. Now, the last set is the set of complex numbers. And the set of complex numbers is a little bit weird when you present it this way. It's the set of A plus IB, where A and B are real numbers, and I is some elements whose square is -1. So this seems a little bit unmotivated. Why would someone be interested in the set of complex numbers, right? In the picture, this is Leopold Kronecker, a German mathematician, who once said that all what we can find in nature are the non-negative integers. Everything else is a human creation. So I'll let you think about that. Now, somehow the conceptual step or understanding of numbers evolved with Khwarizmi, who wrote like a very famous book called Al-Jabr wal-Muqabala, which is a very influential book in the middle 12th or 13th century, and which was the main reference for mathematics in the whole world for like many centuries. And in this book, Al-Khwarizmi showed us how to do some algebraic manipulations, like taught us algebra, like what we do nowadays in middle school or high school, like the fact of adding x and using formal manipulations. We were indebted to Al-Khwarizmi for this. And so Al-Khwarizmi introduced algebraic equations and tried to understand how to solve them in a systematic way. And along the way, all the integers that I introduced before will appear naturally. So for example, if you try to solve the equation x plus n is equal to 0, where n is some integer, well, you realize this equation does not have a solution in integers. You need to introduce the negative integers to solve this equation. Same thing, if you want to solve the equation qx plus p is equal to 0, then you need to introduce rational numbers. So a rational number is a number such that when you multiply it by q, when you add p, you get 0. It's a rather indirect way of defining numbers. Same for some real numbers, like square root of 2. It's the number where when you multiply it by itself, you get the number 2. And finally, now the famous number I, in fact, appeared in the 15th or 16th century among some Italian mathematicians who were trying to solve equations like this, degree 3, and realized that they needed to work with some numbers whose square is -1. But such number cannot be a real number, right? The square of a real number is always positive. And so that's why it's called an imaginary number. Okay, so we'll go back a little bit to, in the picture you have Pythagoras, like Pythagoras. Ça va rappeler des souvenirs du collège. So Pythagoras was interested in this kind of equations, like a squared plus b squared is equal to c squared. So now I showed you like how numbers appeared from equations in one variable. Now I'm interested in more variables. And the most simple example of an equation with many variables is this one, which appeared 500. So Pythagoras lived in this era, so 570 before Christ. And geometrically, this ABC are the sides of side lengths of a triangle of sides A, B, and C. And you're interested in finding integer solution to this equation, or at least that's what Pythagoras was interested in. More generally, this type of equations were vastly studied by this other Greek mathematician called Diophantine, and from which the name Diophantine equations come from. And Diophantine studied more generally, like many, like let's say in 3 variables, like more complicated polynomials than this one, and devised several methods on how to solve them, which some of them are still used nowadays until now. So this is something very fascinating about research in math or math. Like if you prove that something is true, it is going to be true 2,000 years from now. I find that fascinating. And finally, one example of another famous Diophantine equation is this equation of Pierre de Fermat from the 17th century, which is a generalization of this equation of Pythagorean, and where no longer you consider n equals 2, but now here n is bigger than 3, and you ask if there are any solutions to this equation where a, b, and c are non-zero. There's a trivial solution, which is 0, 0, 0, but are there any others? We'll come back to this later. So the general question that we're interested in number theory or algebraic geometry is how do we solve algebraic equations? How do we find solutions which are integers? Well, first we could start by equations with one variable. So just a polynomial, p of x is equal to 0. And we can ask, well, are there any solutions? How can we find them? So the introduction of the complex numbers somehow, or thanks to Gauss, who proved that if you take any polynomial and you try to solve for p of x is equal to 0, you're always going to find a solution in C. So C is what we call algebraically closed. So any polynomial equation has a solution in C. This is really an interesting fact because it tells us somehow C is all what we need to do mathematics. We don't need anything else. That's why I stopped in my first slide in C, and I didn't go further. And now to find solutions for an equation, now there are different methods that I'm sure you've seen and maybe in some exams or problem de concours or in your daily life, where you can study variations. You can do like Newton's method. You start from a point, you draw a tangent, and then you take the image, and you continue so on and so forth, and you can find approximations of the solutions, and at the end, you can try to, if you have like a good enough approximation, try to guess if that solution is an integer or not. So it gives you an approach. There are many ways you could use to try to do that. And anyway, the set of solutions is finite, and yes, so this is what I just said, like you can try to do by approximation, and if you think that there's some integer which is a solution, you can test it, and if it works, then you're in good shape. If not, then it means it doesn't have integer solutions. Now, let's discuss a little bit more this problem of Pythagorean, which is to find integers a, b, and c, which are the side length of a triangle, like right-angled triangle. Okay, so geometrically, like you can try to visualize first what are the triples ABC with real coordinates that satisfy this equation, and you can try to draw them in R3, like f puissance 3. And well, you realize that this looks like a cone. So here, the origin of the cone is the point 0, 0, 0. And then as C grows, if you fix C, then the set of points AB that satisfy this equation is a circle. It's a circle of radius C. Okay. And somehow the solutions with integer coefficient, like where A, B, and C are integers, lie somewhere in this region. Like they're discrete set of points, and you're interested in finding them. Where are they? I'm sure that you've already solved this exercise, like trying to find ABC. Anyone who's already done this exercise before? Again, this is a very classical problem when you start doing arithmetics, and if you haven't done it before, do it tonight. Like this is the problem number 9, right? Is it, or 8 problems in the competition. This is problem number 9. Okay, so I'm going to show you a very easy way. Well, okay, I'm going to show you the way. So you can do it the traditional way. I'm going to show you a very fast way. To find the solutions, first you could divide by c. So, and then you have this equation, x squared plus y squared is equal to 1. And this is the equation of a circle, and now you would like to find x and y rationals. So here's what you could do. You can first draw the circle of radius 1. And now you can, in the circle, you have the point of coordinates 0, minus 1. And then each time you have a point x, y that satisfy this equation, you can draw the line that join this point and 0 and minus 1. So this line will intersect the x-axis in a unique point, which coordinate is something comma 0. And because you started with everything with rational coordinates, so this line has rational slope, like une pente rationnelle, donc les coefficients y is equal ax plus b of this line are all rational numbers. So it intersects this line in a rational number. And now we can reverse the process. You can first start from a point here which has rational coordinates, let's say P over Q, compute this line, compute its intersection. It's going to intersect the circle in a unique other point. And then you can just compute what are those coordinates. And if you do the computation, you arrive, okay, this is an exercise. You can do the computation, and then you get this solutions. Like x is 2pq divided by this, and y is p squared minus q squared divided by this. And so when you remove the denominators, then you get that's all these triples ABC out of this form. Who have seen this before? Raise your hand. You've already seen this result before, right? Okay. Did you do it this way? No. Okay. So this is a very fast way to solve this exercise, and it's yeah, very conceptual. Now, if you have already done this exercise for 2 variables, you can try to do it for many variables. And again, it's the same idea. Okay, like try to find all the, well, n+1 tuples, x1, xn, and z, which satisfy this equation. So that's an exercise for you. Okay, so now I'm interested in a more complicated set of algebraic equations. So I have many polynomials, P1 until PR, with n variables. And I want to understand what is the set of solutions of this system of equations. So the P1 until PR could be of any degree. If they could be, for example, just of degree 1, and then you're in the field of linear programming, like a lot of artificial intelligence, like software, like start from here, or at least in the some ideas from are used. More generally, it could be like any degrees and any complexity. And you want to say something about this, right? Try to solve it. Yeah, so as I said, the PIs are some polynomials. Like, for example, they could be a sum of squares if you're interested in some minimization problem, or it could be basically anything. Think about any polynomial that it could appear here. And the general problem is, what can we say about this system of equations? Like, can we find general methods to try to understand and solve this type of problems? And this is roughly what algebraic geometry and number theory is interested in. Like, try to like craft or like come with general methods, algorithms, processes that if you have a specific problem, you can use them to solve your problem. It could be a problem in math, but it could be also a problem in applications of math to other disciplines. So for example, here, I've drawn in R3 the set of solutions to this equation. You see, it's usually something complicated. Look at the solutions in C to the power n. What happens is that usually is going to be a shape which is continuous. You know, imagine a sphere. A sphere, there's like no, it's like a continuous object. In general, it's going to look at something that is continuous. And this is what we call an algebraic variety. Okay, so an algebraic variety is like just a subset. You can think about it, just a subset of C to the power n, which is the zero, like such that all its points satisfy a system of polynomial equations. Any questions? English is okay. Français? Yes. So yeah, that's a good question. So here I can allow any real numbers or even complex numbers. But if I want to do number theory or arithmetic, I usually would like them to be integers. Yes. As an algebraic variety. Well, you just take the what? Yeah, do you want to take the microphone?
I asked about how we can represent C power n.
As an algebraic variety.
Yes. Like for presenting like something, a graph or something like that, in like a plan or un espace, on peut visualiser ça, mais avec un ensemble, c'est la puissance n, c'est un peu difficile. Comment on peut le faire?
Oh, like geometrically in your head. Oh, that's very hard. I don't know what to say. You just, in general, we have the intuition for what happens in dimension 2 and 3, and then everything happens in your head afterwards. Okay, so now the set of integer solutions, if these PIs have integer coefficients, in general, you can imagine them as just some discrete subset, like there's going to be 1 point here, 1 point here, 1 point here, and you would like to know how many there are. How can you find them in an effective way? Maybe sometimes they're empty, like there's nothing, as we can see in the Fermat problem. So these are all questions that as algebraic geometers and number theorists try to answer. Now, let me start with some negative results. So in the picture here, this is David Hilbert, probably one of the most famous mathematicians in the beginning of the 20th century. In 1900, Hilbert made a list of 23 problems, and he decided these are the most important problems everyone should think about. And there's problem number 10, which asks, can you find a universal algorithm such that given a set of polynomials, this algorithm will tell you they have a solution or they don't have a solution. Okay, this is like very, it seems very optimistic, and it's in fact too optimistic to be true. 60 years later, well, after the work of many people, the answer came from Yuri Matyasevich, like a Russian mathematician, who proved that such algorithm cannot exist. So think about it, like he proved that you cannot find a way to decide if a given set of polynomial equations has a solution or not. It gives headache just to think about it, rather think about proving it. So the conclusion is there's no general method to decide, or I mean, provably, we can prove that there is no general method to decide whether a system of polynomial equations has a solution or not. And so this is, well, a bit sad, right? Well, we do as much as we can. And next, I would like to talk about a very well-studied class of examples. These are called elliptic curves. And these are like maybe one of the simple equations you could imagine. So here I'm considering the following equation in y and x, where y squared is equal to x cubed minus 4x plus 1. I just took this as an example, but you can take here any coefficient, here another coefficient, and you're going to get something that we call in math an elliptic curve. I'm talking about this example for a reason. You're going to see that at the end, they are the center of many, many recent developments in like modern math. And if you try to plot, or like draw this set of points in the plane in R2, which satisfy this equation, you realize it looks at something like this. There's like some circle here, and there's something here. But this is if I draw it in R2, like x, y are real numbers. Now I can try to look at the solutions in C2. So I look at the pairs y and x, which satisfy these equations and which have complex coefficients, right? Complex numbers that are linked by this relation. Then what I get is something that looks like this. So the set of points in C2 that satisfy this equation looks like a donut, bini, sphincter. So this is not very easy to see. You have to work a little bit to prove that it looks like this. Like maybe a class of complex analysis, like an analysis complex at the end, like you can prove this fact, but it's doable. And so now arithmetic will be interested in finding the sets of like what I call EQ and EZ, which are the solutions of these equations, which have either rational coordinate or integer coordinate or integer coefficient. So this is like I want to illustrate like the main ideas in this specific example, like how can we find solutions of this very simple equation like in this setting. In fact, we know already a result of Siegel, another German mathematician, who proved that there are only finitely many solutions with integer coefficients. You can only many numbers with z entries that satisfy this equation. This is like highly non-trivial. Like for example, for the Pythagorean equation, we found that there are infinitely many, right? We found, remember, a couple of slides ago, we found all like this triples, and so there are infinitely many solutions. And here, what Ziegel proved is that there are only finitely many solutions if you look at the solution, like if you restrict to x and y being integers. But it's okay. We can try now to understand the solutions which have rational coordinate. Now, something nice which is interesting about this elliptic curves is that if you look at like just this set of solutions with c coefficients, it is a group. Everyone sees what a group is? Raise your hand if you don't, or if you do. Like think about it just as a vector space. Loosely speaking, just like as a vector space. Well, you probably know vector space after knowing group. It's a group. And the addition law is very geometric. If you take 2 points P and Q and you try to add them, what you do is that you take this point P, you take this point Q, you draw the line between the two. It's going to intersect this curve in a third point. And then you take the reflection with respect to the x-axis, and you get another point which we call R. And now you define R is the sum of P and Q. It's a very exotic operation. Like when you add 2 plus 3, you know it's going to be 5. Now, if you take two solutions of this equation, I've given you a recipe to say how can you add them to obtain a new solution. And this is very interesting, right? For example, if you want to add P plus P, you just take the tangents at P, and then you intersect it here, and then you do then the reflection, and then you obtain 2 times P. And so you can do this like every point, like you can add this and add this and add it to itself. And this way you can generate a lot of solutions. If you just have one solution, you can start adding it to itself, and you obtain more and more solutions. Well, sometimes you're gonna obtain infinitely many solutions, but sometimes you're gonna obtain finitely many. And this is expressed by the idea that this group of solutions, because of this group structure, it is going to be something like z to the power r. So think about this as you have like some kind of basis of solutions, like the same way a C vector space has a basis. Here, there's going to be a basis of solutions, and some extra terms, like which is usually going to be a finite abelian group, like something like a z mod pz or like a z sur n z. Okay. Well, yeah, we do both these facts to these two mathematicians, so André Weil, French mathematician, and Louis Mordel. Well, you don't see him very well, but British mathematician. And they almost did this a century ago. Like this observation or this construction is like maybe 100 years old. And in fact, the interests of this construction of the elliptic curves has been like they have been shown to be very useful when it comes to securing communication in internet, like encryption. Like usually when you send a message over Facebook or like you use your credit card to pay a transaction online, you need to be sure that nobody is going to come and steal your information. And so this picture that I've taken from the Academy of Sciences of the United States, they have done a series of pictures. I will show you another one at the end, and I can give you the reference if you want to look more. You see like the tree of like internet security, like from the basics or like the fundamentals to the most cutting edge like technologies to ensure that everything you do online is secure and there's no hackers trying to steal your data. I mean, this is also important for economy, for big corporations, like everyone wants safety online. And if one of the trees of or like one of the roots of this tree you see here, it's algebra on elliptic curves. So this very abstract object that I have just introduced is in fact one of the cornerstones in modern like encryption and or modern cryptography. And briefly how this works, so let me just give you really a brief idea. The most classically used system in cryptography is what's called RSA, like Ron, Shamir, Adelman system. And so there is a sender, there's a receiver. The sender wants to send a message, but they need a way to encrypt this message. And the receiver has a way of decrypting this message. So what usually happens is that the receiver has some public key, like if you want to send me a message, here's how you should do. And they give you some numbers. And the sender used that to send the message. And then the receiver used like the private key to decrypt that message. Like, just to give you a brief idea, the security of this system relies. Okay, I've added like maybe some technical explanations, but let me not talk about them. But the security, like why this works, is the difficulty to factor a given integer into a product of two primes. The idea is very simple. So you have to choose two large prime numbers, compute their product, and this is going to be the public key. So if somebody intercepts this public key, they will need to factor n as a product of p and q. And this is a very hard computational problem, especially when the prime numbers involved have they're of order 2 to the power 1024. So they have 300 or more digits. So imagine a prime number avec 300 chiffres. And then you multiply it with another prime number with 300 chiffres. And then that's the number you get. And you want to factor that. That's a very hard problem. You can think about it. If you can solve it, then, well, you should come see me. Before going to Google. So there are difficulties with the system. First, you have to find very large prime numbers, and this is not easy. Like there's no known algorithm that gives you like big prime numbers. And now with the emergence of quantum computers, like notably what's called the Shor's algorithm, there's a real risk that all these algorithms are going to become useless. Like if quantum computers were to be developed, then security online will be the biggest threat. It's going to be very hard. And so conclusion, like a secured encryption protocols are needed and they are vital for our online communication. Like nowadays, everything happens online. And so we want to be prepared if quantum computers were to be developed or like some sophisticated hackers develop new techniques, the encryption algorithms are always ahead. Elliptic curves actually were used or like started to be used for this purpose. Like the difficulty comes from, or like why this works, is that this group here that I showed you, well, because of this very complicated addition operation, it makes this group to describe in practice very hard. Like you can't like to find solutions and like to like do this additions, like it's very computationally heavy. So if a hacker were, so what usually happens rather is that public keys is you have some point in this elliptic curve and you multiply it a number of times. And it's very difficult to reverse this process. There's like no logarithm. Like if you have x to the power n, usually in real numbers, you take the log and you have access to n. For elliptic curves, it's a very hard process because there's no logarithm. And this is what's called the discrete logarithm problem, and why like cryptography with the elliptic curves works. So usually, if you connect online, you're going to see either like ECC, encryption like with elliptic curves, or RSA, like encryption with the other system I described. And so far, these are the most widely used systems. Now, the advantage of this, here I've introduced a picture of Tahir al-Jamal, an Egyptian mathematician who was the first to devise this algorithm, like to find this algorithm to do cryptography with elliptic curves. The advantage is that you only need small numbers, a and b. Like earlier, I introduced like -4x + 1. In general, you only need 256 bits, like 2 to the power 256 to do this operation, compared to 3000 if you want to do it with RSA. So there is real advantage. So I think the point of these two slides is that there are a lot of things that are done in like pure math, what we call pure math, that have a lot of applications in other disciplines. They are just waiting to see that day. And the structures and were all understood 100 years ago. We only started using them now to understand encryption. Okay. Now, my next topic is, so I'll talk to you a little bit about elliptic curves. I want to describe a very special class of algebraic varieties, which are algebraic curves, which are also like very well studied. And of which elliptic curves is a particular example. So now consider if you have like a system of algebraic equations. Let's say you have R equations and n variables. And at the end, when you try to solve them, you realize you have only one free variable. So one free variable somehow describes this whole system. Then in that case, this algebraic variety is what we call a curve. And it's exactly what you imagine in your head, what you picture. A curve is something of dimension 1. So you only need one complex variable to describe an algebraic curve. Now you can try, this resolution is not great. You can try to understand the topology of an algebraic curve. So in the title of my talk, there was topology and arithmetic of algebraic varieties. So what do we mean by topology? We mean roughly the shape. Like, what do algebraic varieties look like? And in the case of curves, because they're dimension 1 over c, they have two real dimensions. So if you want to describe them using R, it's 2 dimensions. Oh, sorry. And in fact, algebraic curves, or the shape of an algebraic curve is completely understood. It's going to depend only on the number of holes that this surface has. And it's either it doesn't have any holes, so this one and this one, topologically, we see them as the same. So topology is really the science of shapes. And if you deform it a little bit, that doesn't matter. Like, it's still the same shape. So for example, this one and this one is the same shape. This one and this one is the same shape. Think about it. Like how to go from a cup of coffee to a donut. Like just by continuous deformation and without breaking anything and without disconnecting anything. Oh, sorry. Without breaking anything and without disconnecting anything, you can go from here to here. And same for, like, you know, if you have 2 holes, you can go from this shape here to this shape here. Oh, sorry. No, this is G equal 3. From G equal 2, like you have 2. And then you can imagine you do deformations, and it's all going to be the same thing. Now here, G equals 3. So there's one integer that matters when it comes to topology. It's just this number, G. Now, without getting too much into details, like this G equals 0 is what we call spherical geometry because they look like spheres. For G equal 1, this is exactly the elliptic curves that I have just described for you earlier, and what we call flat geometry because locally they look like flat, there is no curvature. And then for G bigger than 2, these are called hyperbolic geometry. So this is like a very interesting geometry that wasn't studied until like Riemann in the 19th century. Okay, so now let's come back to our problem, which is if you have an algebraic curve, so a system of polynomial equations with one free variable, can you find solutions with integers or like with rational coefficients? Any questions before I? Yes. Yeah. The what? Uh-huh. Yeah. Okay, like with the rational, yeah. Okay. Bien sûr, oui, tout à fait. Oui, pour simplifier, bien sûr, tout à fait. Oui, merci pour la remarque. Donc, la remarque, c'est que le groupe Adalena, le T, on peut le simplifier encore plus comme une somme de Z sur NZ. Ça va être une somme de plusieurs Z sur NZ. Ouais, merci. Donc, le problème, c'est est-ce qu'on peut trouver les solutions à coefficient T liées à les cours? Alors déjà, ce qui est vraiment surprenant, c'est que la réponse dépend de la topologie. Et ça, c'est un aspect que je trouve très fascinant une géométrie algébrique aux théories des nombres, c'est que finalement, les deux, ils sont très reliés. La topologie ou l'arithmétique, c'est très, très relié. Donc, la réponse, s'il y a des points à coordonnées, on va dire Z ou Q, elle dépend beaucoup des clantiers G, le nombre de trous, qui est une information topologique. Et en fait, ce qui se passe, c'est que pour G égale 0, les points rationnels, soit c'est it's either empty, there's nothing, or it's dense. And the way you show it's dense is exactly the same way. If you have a sphere and you only have one point, then you can start projecting from that point using lines. Like take one line with rational slope, and you construct an intersected with the sphere, you construct another one. My point is here. And then take another line, you intersect it, and so on and so forth. And you see that you're going to construct a lot of other solutions just by this very simple geometric way. For G equal 1, it's an elliptic curve. The answer depends on that R that you saw earlier, 0 to the power R. If R is 0, then it's finite. If R is bigger than 1, it's infinite. So it's somehow the good transition case. And then for G bigger than 3, it is, in fact, an amazing theorem due to this person, Gerd-Faltings, that it's always finite. This result was conjectured for 80 years. People expected it to be true. It's proved in some special cases, but nobody could prove it until Faltings proved it, and it earned him the Fields Medal. So it's really a result worth the Fields Medal. To tell you how difficult this topic is, like just to prove that there are finitely many solutions, you can earn a Fields Medal for that. Okay, now, if you can't really, if you're stuck and you can't do anything, you can try to do the following. Oh, yeah, sorry, G bigger than 2. Yeah, here. Yeah. There's a typo here. Here it should be G bigger than 2. Yeah, thank you. Very observant. Now, if you can't do anything and you want to still like think about your problem and try to do something, you can find approximate solutions in integers always. And how this works is that you can try to find integers x and y such that instead of having equal to 0, you want it to be equal to 0 modulo p. Like fix a prime number p and try to find all x and y such that p divides this quantity. And then you can count, how many x and y's there are such that this is equal to 0 modulo p. And you can do it just by brute force. For example, you can just take all x and y, which represent a complete set of residues modulo p from 0 to p minus 1, and compute and see if you get 0 modulo p or not. And so this number of solutions, I denoted here as p plus 1 minus mp for a specific reason. This AP was shown that it satisfies this following bound. You can ignore this for now. And so, in fact, this is like more from a computational point of view. If you're trying to compute all the solutions, you can just do it in a brute way. And then once you get the number of solutions that satisfies this bound, then you're done. So this is the naive approach. Of course, there's like some more sophisticated approach. I'm not going to talk about like the Schuf algorithms, Schuf-Elke-Zatkin algorithm. There are like really a lot of research on how to compute this number of solutions in an efficient way. So all what I want you to understand from this slide is that if you are really stuck and you don't know what to do, you can always try to reduce modulo p and understand what happens there. Yeah, question? So we need prime number, well, usually because any integer is a product of primes. And so prime numbers are the simple ones for which you can do this. And you're going to see the reason also appearing right now is that, so for each prime p now, we have counted the number of solutions, and it's p plus 1 minus ap. Okay, I denote it this way. And what you could do is put them in this infinite product. So it's a function in S. This may scare some of you, but let me assure you, it's a very simple operation. You just take the following fraction, 1 minus ap times p to the power minus s plus p to the power 1 minus 2s. So p is the prime number. ap is this number here. And then, well, not p from equal 1, but p from equal 2 to infinity, the product of all primes. And now this is a function of S. It reminds you, does it remind you of any like function, like famous function? Riemann zeta function, yes. In fact, this is a generalization of the Riemann zeta function. Like there are like a lot of ways you can generalize Riemann zeta functions, and this is one of them. And this is called the L function of the elliptic curve. Now, if you don't know what holomorphic is, it's okay. You can just take S, a real number, and then this is going to be a function which is like a differentiable function when S is bigger than 3/2, if you wish. And then if you know what holomorphic is, then you understand what this means. But so this is a function for S bigger than 3/2 is differentiable. And now for a long time, the conjecture was, can you extend this function on all the real line? Like instead of having it just for S bigger than 3/2, could you extend it for, let's say, S equal -1, S equal -3? And this is a very hard problem. It's not easy. It might sound easy, but it's not. In fact, it's a consequence of Andrew Wiles' proof of Fermat's theorem. The fact that you can extend it to the whole complex plane. So under this theorem of Wiles, this L function, you can extend it to the whole complex plane. And what happens is that at S equal 1, it will vanish. Like L of 1 is maybe it will vanish, maybe it will not, but you can always find an equivalent, like L of S is equivalent to S minus 1 to the power some integer, when S is close to 1. So this is an asymptotic behavior when S is closer to 1. And this integer here is called the analytic rank of the elliptic curve. Now remember, we have already introduced another R. The R such that E of Q is Z to the power R times T. And this R here is called the algebraic rank. So we have two integers. And you can all guess what's the next conjecture is going to be. Are they equal? This is maybe one of the hardest problems in math right now. It's what's called a millennium problem. So it's in 2000, the Clay Mathematics Institute had a meeting and decided what are the most important problems in the 21st century. Each of them has $1 million prize, and this is one of them. So if you want to make $1 million, you can try to solve this problem. And it's probably one of the hardest way to make $1 million. So in fact, except when this rank is less than 1, this conjecture is not known at all. Like there's no result, nothing is known. And as I said, this is one of the millennium problems. Okay, so I don't have a lot of time left. Let me come back now to Fermat's theorem. Fermat, in 1637, 1737, he claimed to solve this equation. You probably all know the story. He has this book from Diophantine, and he wrote on the margin that he found the solution, but the margin was too small to write the solution. Well, 300 years later, we don't know what that solution, we don't know what the solution could have been. In fact, the breakthrough, or like the solution of this conjecture came thanks, well, to Andrew Wiles, but also the work of many people before him around 1995. So this is really one of the greatest achievements in the last, at the end of the 21st century in math, is like the solution of this problem. And Wiles proved that Fermat's equation does not admit non-trivial solutions in integers when n is bigger than 3. Well, solutions could not have been found by Fermat because it used so much sophisticated mathematics that took hundreds of years to be developed, and so it's impossible that Fermat could have known about that. Well, let me give you all otherwise proof in one slide. Wait. So assume you can find like a non-trivial solution, ABC. The starting point is that, and this is something that was conjectured by this group of three mathematicians, Taniyama, Shimura, and Weil, is that every elliptic curve is modular. So I introduced an elliptic curve before. I showed you it has an equation y squared is equal x cubed plus ax plus b. And the question is like, how can you find solutions of this elliptic curve? And those people conjectured that there is like a canonical way to find these solutions. And that's what modular means. But then Freyr noticed that if you take a pair of solutions and you consider this specific elliptic curve, then it has really strange properties. Like it would contradict this modularity. Here I took the elliptic curves, x times x minus a to the power n times x plus b to the power n. So when you develop, you will get an equation y squared is equal to x cubed plus something times x squared plus something times x plus something, right? You get a polynomial in x of degree 3. This has been made more precise thanks to the work of Jean-Pierre Serre and Kenneth Ribet from professor at Berkeley, and Jean-Pierre Serre, professor at Collège de France. And they linked like this Frey curve to modularity of elliptic curve. They made like a very precise and clean statement that needs to be proved to solve Fermat's problem. And this is indeed what Wiles did. He proved this modularity statement, or like this result. So obviously, I'm not going to go into much details, but just to show you that there are many people that were involved in this process, and it took maybe like 50 years of discussions back and forth to get the final result. Okay, so my last slide is, or my one before the last is, what is current research in algebraic geometry and number theory looks like. In the picture, Alexander Grothendieck, probably one of the most famous algebraic geometers of the 20th century, a very fascinating life story. And by himself, he rewrote the entire algebraic geometry of the 20th century. Him and his school probably wrote thousands and thousands of pages to give like new foundations for algebraic geometry, like very solid ones everyone uses nowadays. And then suddenly decided to quit math and go live in the mountains for the last 20 years of his life. So it's a very interesting life story. So one of the objects of algebraic geometry is to classify algebraic varieties. So I showed you like for curves, they're like the specific shapes, like the number of holes. Now, can you give a general classification of all algebraic varieties? We can like also interested in finding like the solutions in integer points, and this is a field which is called Diophantine geometry, and this is like in number theory, so it's an interaction between the two. Also attach topological invariants to algebraic varieties. So before I showed you that you can attach the number G, but in general, there are like many things you can do with this is what's called homology and cohomology groups. In the picture, Peter Scholz, German mathematician, who in fact constructed many cohomology and homology theories to study algebraic varieties, and it's earned him the Fields Medal in 2018. It's very deep and influential work. And the goal, yes, is to understand the shape and the topology of algebraic varieties, like how do they look like. There's like a dream also among mathematicians is like, can you decompose every variety?
you very much, Salim. So we have quite a few minutes for questions. So if you have any questions, just raise your hand. You can ask questions in any language provided. Professor Tayou speaks it also.
Yeah. Spanish is okay. No.
Salam alaikum.
Ouais,
Déjà, je crois que la présentation, c'était très intéressant. La question, généralement, quand définir la structure de groupe de modèle à les points rationnels, pour chaque droite, 3 intersections. L'autre, on prend 2 points et on prend le symétrique du 3e point.
Ouais.
Dans certains cas, par exemple, une droite verticale, on a seulement 2 intersections. Donc, comment on peut définir le 3e point?
Très bonne question. C'est en fait ce que je décris, c'est que ça fait de points à l'infini. Donc, tu fais dans le cadre de la géométrie projective.
You said earlier that a Russian mathematician proved that there is no algorithm that can give you if a polynomial equation has a general solution. How do you go about proving such a thing? How do you prove that you cannot? How do you prove that a solution does not exist? Like, how do we know that it's just we haven't just come up with it yet, or how do we know it's impossible? It's impossible to find one.
Yeah, no, that's a very good question. And usually the way these proofs go, like you assume first you have to formalize the problem very well. Like you want to have like a clear statement, like what do you mean by this question? The way I said it is a little bit vague, but you want to say, okay, there is like maybe a Turing machine or like an algorithm such that as input, you give it like a set of integers, and as output, it tells you an answer, yes or no. Like, does it have a solution or not? And usually you do this by contradiction. Assume you can find such way of doing this. And then in general, there's like a lot of steps. I don't know that field very well, but there's a lot of hard work to show that if you assume that there is such thing, then you can contradict something along the way, either like, for example, Gödel incompleteness theorem, like which is like one of also one of the very famous theorems of the early 20th century, which says that there are some theorems or like some statements which you can prove that you cannot prove them. Like you prove that they're not, you cannot prove they are true, and you cannot prove they are false. And so this is the kind of contradiction like that comes from logic theory that this kind of proofs use.
السلام عليكم، شكرا
وعليكم
على
السلام.
البرزنطاسيون.
شكرا.
عندي واحد السؤال. دابا كنعرفوا ان مثلا كيو ولا زد كنقدروا نكونستريوهم بلي ريلاسيون بينير. واش عندنا الكاباسيتي باش نكرييو اي انسومبل ا ليد ديال لي ريلاسيون بينير ولا كاين شي ديفيكولتي؟
Le fait que la construction de QZ par des relations binaires, Q, c'est le corps des fractions de Z. Donc, c'est la relation dès que tu veux identifier A sur B avec C sur D. Et la manière de le faire, c'est A sur B égale à C sur D, si AD moins BC égale à 0. C'est ça la relation binaire que tu introduis à la Z croix Z pour construire Q. En général, c'est que tu dois partir quelque chose tu dois partir de quelque chose pour faire de la relation binaire. Pour construire R, tu peux pas partir de R lui-même, parce que c'est un ensemble plus petit, par exemple Q, et tu regardes les suites de Cauchy, Q, et tu quotientes par la relation d'équivalence deux suites de Cauchy ont la même, sont proches. Et comme ça, tu construis R. Donc, voilà, il y a des manières. Je ne pense pas qu'il y ait de méthode générale, à part si tu fais une relation triviale. Il n'y a pas de méthode générale pour le faire, mais pour chaque problème, tu dois identifier quelle est la bonne manière de le faire. À حسب le besoin, à حسب شنو ensemble tu regardes. Il n'y a pas de méthode générale. Ou des fois, si tu as une construction directe, tu n'as pas besoin de passer par des relations d'équivalence. C'est mieux s'il y a une relation directe.
شكرا.
Salam alaikum, Al-Hajj Amri. Je suis pas l'élève, je suis un prof, peut-être ici c'est le plus vieux. Alors, je voudrais dire deux choses. Alors, tout d'abord, je voudrais vraiment féliciter les organisateurs à la Chilkeidiro, que j'admire. Et franchement, nous, les seniors, on n'a pas pu le faire. Au moins, ils sont en train de le faire. Je leur souhaite vraiment. Je leur félicite pour ce travail extraordinaire. Et Rarasu, Akaltum, Wagadan, Rosule, Kulul Akharoun.
On les applaudit. Hein.
Donc, vraiment, bravo, bravo. Et je voudrais vous remercier, professeur Salim Tayou, pour cet extraordinaire voyage, cette pédagogie. Et je me permets de vous raconter une petite histoire à propos de la conjecture de Chimera Tanyama-Weil. Quand Wales a fait sa démonstration, il y avait un essai à Ulm de Serre, Austerley, pour présenter la démonstration, qui est très, très difficile. Hein. C'est à peu près 1000 pages, mais c'est de deux spécialistes de domaine. Et Jean-Pierre Serre, il racontait qu'André Weil, il voulait donner ça comme question dans un master. À l'époque, ça s'appelait DEWA, un examen de DEWA. Et il a demandé à Serre, qu'en penses-tu si je donne ça? Il lui dit, attention, je n'ai pas d'idée, donc je me demande comment un élève de master va faire ça. Donc voilà, les maths, c'est vraiment une construction et il faut voir le long terme et il faut pouvoir bénéficier de conférences comme celle qu'a donnée Salim et qui va donner Reda Al-Araqi. Et bravo encore aux organisateurs. Voilà. Merci.
Merci.
Since 1995, have there been other proofs published about Fermat's last theorem to demonstrate Fermat's last theorem?
Other ways of proving it?
Yeah.
No.
So it's the only one we have?
Not to my knowledge, no. Maybe someday. I see a lot of young people here. Inshallah.
First, I want to thank you. The question is دويت على الكريبتاج في الدومين ديالو. بغيت نعرف واش حتى الهاشين حتى هو كيخدموا فيه التوبولوجي ou le variety algebra.
Alors c'est une très bonne question. La réponse est je ne sais pas, mais je peux revenir à le diagramme que j'ai montré. Donc, si tu vois ici, donc hash functions, c'est tout en haut c'est autour de l'arbre. Et si tu redescends, tu vas te retrouver l'algèbre des courbes elliptiques. Donc, d'après ce diagramme, on peut penser que oui, mais moi, je ne suis pas spécialiste là-dedans.
Bonjour, alors je voudrais tout d'abord vous remercier pour la présentation. Bon, ne me prenez pas au mot, je ne suis pas spécialiste, mais enfin, je ne connais pas beaucoup dans le domaine. Mais je voulais juste parler de l'extension de la fonction de Riemann. Là, vous avez parlé de LS, le produit infini des nombres premiers. Il y a aussi la suite à AP qui apparaît. Et on connaît on connaît l'expression de la fonction zeta, son extension dans C, et par unicité de l'extension, est-ce qu'on ne peut pas avoir quelques informations sur les AP que vous avez présentées?
Non, parce que la fonction zeta de Riemann, quand vous l'écrivez en produit, c'est le produit des P, des 1 sur 1 moins 1 sur P à la puissance S. Donc, il n'y a pas de AP qui apparaissent, il y a juste 1 moins P à la puissance moins S. Alors que les AP ici que j'ai définis, ils sont définis pour chaque nombre premier P, si tu comptes le nombre de solutions modulo P. Il y a la courbe elliptique. Donc, des nombres de paires x et y qui satisferont l'équation et tu fais P plus 1, tu les écris comme P plus 1 moins AP, dès que le AP, c'est relié avec le comptage local. Donc, ça va changer pour chaque courbe elliptique d'RTTA. Le AP, il va changer. Donc, en fonction des coefficients, donc moi, j'ai pris y au carré égale x cube moins 4x plus 1. Si j'avais pris moins 5x plus 10, les AP, pour chaque nombre de P, ils vont être différents. Donc, ils dépendent de chaque courbe elliptique. Et, voilà.
Généralité, vous savez que la géométrie algébrique a été introduite par les mathématiciens arabes. Vous savez que les Arabes, ils ont résolu l'équation de second degré, ils avaient beaucoup de difficultés à résoudre l'équation de troisième degré. Donc, ça a été résolu par les Italiens au 15e ou 16e siècle. Mais comme on dit en arabe, à partir de ce moment-là, ils ne sont pas restés les bras croisés. Ils ont introduit la géométrie algébrique en résolvant les équations à l'aide des courbes. Et après, ça restait un vrai problème. Ils voulaient faire des approximations. Et d'après un livre de Jan Pfeiffer et quelque chose d'Almedeco, ils ont introduit la méthode des approximations successives, qu'on appelle aujourd'hui le théorème de point fixe, approximation successive, pour réussir à trouver des approximations des solutions. Donc, les Arabes, ils ont bien fait, et vous savez qu'on n'est pas loin de Marrakech, et Benoul Benna, et le prof de son prof, Moun'im, ont introduit l'analyse combinatoire. Ce qui veut dire que l'analyse combinatoire est une science marrakchienne. D'accord? Donc, vous, Allah, j'espère que vous serez de grands mathématiciens, de grands scientifiques, et vous faites des choses. Vous honorez les Arabes, vous honorez des conférences comme celle-là, et des organisateurs comme les organisateurs de Maths Maroc. Merci.
Merci pour la note historique. Vous êtes les héritiers et les héritières des traditions.
Il y a RSA et puis il y a l'autre pour les Elliptic curves. Là, ce que je connais, ça consiste à prendre un très grand nombre et voir sa factorisation en nombre premier, en deux nombres premiers, alors que l'autre, c'est plus des nombres rationnels qui interviennent. Je me demande, est-ce que c'est plus difficile, plus compliqué, elliptic curves, la méthode, le chiffrement used in elliptic curves, que le chiffrement RSA? Y a-t-il plus de difficultés, de complexité ou autre?
D'accord, merci pour la question. Donc, voilà, ce qui se passe quand on fait le cryptographie par les courbes elliptiques, c'est que finalement, on n'a pas besoin de prendre avec les entiers A et B très très grands pour arriver à la même degré de complexité que RSA. C'est-à-dire que la structure, le groupe avec les solutions rationnelles est suffisamment compliqué. Tu vois, avec les opérations, tu prends 2 points, tu prends la droite, et puis tu prends la symétrique, et ainsi de suite. Ça, c'est des opérations, si tu les fais, c'est relativement facile, mais pour les reverser le processus, si tu es un pirate et que tu interceptes le message, pour faire le chemin inverse, c'est très, très difficile. C'est là où repose l'intérêt de la cryptographie par les courbes elliptiques. Ce qui fait que tu peux prendre des nombres petits, A et B, l'équation, et le processus inverse, si tu prends une solution, tu la multiplies, tu veux faire le processus inverse, ça va être aussi compliqué que si tu avais pris des nombres premiers RSA de l'ordre avec 300 chiffres, là, avec 400 chiffres. C'est ça l'intérêt de la méthode, c'est que c'est un intérêt calculatoire. Donc, ouais, voilà.
Hello, Professor. I just noticed in one of your slides that you said for those mathematicians for given problem, they proved that there is an algorithm to do it. I'm just wondering that how can you prove that there is no algorithm to do something?
D'accord, merci pour la question. Donc, la méthode, comment ça se passe, le genre de preuve, en fait, ça remonte vraiment le début du XXe siècle avec l'introduction de la formalisation de maths. D'abord, il faut bien formaliser le problème. Qu'est-ce qu'on veut dire par il n'existe pas de processus qui, en entrée, te donne, tu lui donnes en entrée des nombres et à la sortie, il te dit si l'équation qui est déterminée par les nombres a des solutions ou pas. Donc, il faut d'abord bien formaliser le problème. Et ensuite, c'est par contradiction. Donc, je suppose qu'il y a un algorithme qui résout tous les problèmes et c'est ce qu'on appelle des problèmes d'autoréférence. Donc, ça, c'est par exemple apparu dans les preuves de Gödel, quand il a démontré par exemple l'incomplétude de l'arithmétique de Peano, les systèmes d'arithmétique, il est incomplet. Ça veut dire qu'il y a des énoncés que tu peux formuler, que tu peux comprendre, mais tu ne peux pas prouver les énoncés, ils sont, ou là tu prouves que les énoncés, ils ne sont pas prouvables. Tu prouves que tu ne peux pas prouver qu'ils sont vrais, ou tu prouves que tu ne peux pas prouver qu'ils sont faux. Et voilà, en fait, le nœud de la méthode s'appelle des méthodes d'autoréférence. Si tu penses un peu, c'est un peu les paradoxes classiques. كاين واحد المدينه اللي فيها واحد الحلاق كيحلق غير الناس اللي ما كيحلقوش راسهم. C'est déjà conseillé peut-être à ça. Ça, c'est un paradoxe. Et donc, tu arrives forcément à un moment donné à ce genre de paradoxe si tu supposes qu'il y a des machines universelles qui peuvent tout faire. Alors, ils peuvent tout faire et rien faire, et tu fais des arguments pour les référencer à elles-mêmes, et à la fin, tu arrives à des contradictions.
Monsieur, merci pour la présentation et pour ce recherche. Et je veux poser une question à relier avec la raison. Est-ce que la méthode, ce n'est pas, on n'a pas une méthode pour donner une réponse déterministe. Non ou oui. Donc 1 ou 0. On ne peut pas formaliser une méthode pour donner la probabilité que ce système de polynômes, il y a une solution entière ou non.
Le problème avec les probabilités, c'est tu peux formuler que c'est 50% oui ou non, mais ça ne veut pas dire grand-chose si tu cherches une solution. Et il faut donner un sens à 50%. Ça veut dire, qu'est-ce que ça veut dire que tu as une chance de 50% de trouver une solution? C'est quoi ton espace de probabilité? C'est l'espace de toutes les équations algébriques, l'espace de tous les coefficients des équations algébriques, tu dois mettre une mesure dessus. Et ensuite, tu arrives au même problème, c'est que tu dois démontrer que l'ensemble des équations qui admettent des solutions, c'est quelque chose qui détermine, c'est quelque chose de mesurable, tu dois calculer sa mesure. Ça va être ça la probabilité.
Oui,
mais ça veut dire que tu as une méthode de déterminer c'est quoi avec l'ensemble au sein de tous les ensembles des équations algébriques, et tu arrives au même problème.
On peut étudier l'ensemble, un sous-ensemble mesurable des équations. Puis on étudie dans ce.
Après, si tu te restreins juste à l'ensemble des équations qui ont une solution, tu vas avoir 100% des équations.
Ce n'est pas une équation qui a une solution. On a faire par exemple par exemple, on montre, c'est un fermé, c'est l'ensemble des solutions, c'est un fermé, donc elle est en particulier
après, il faut faire la distinction. Est-ce que tu prends une équation et tu regardes ses solutions, l'espace incarné, ou est-ce que tu regardes l'espace de toutes les équations? Qu'est-ce que ça veut dire l'espace de toutes les équations? C'est que tu regardes les coefficients de les équations, et ces coefficients-là, tu les mets dans un nouveau espace qui est très très grand. Et à l'intérieur de ces espaces, tu regardes tous les coefficients, enfin tous les nombres qui sont coefficients d'un système d'équations polynomiales qui admettent une solution. C'est aussi que la complexité est grandie. Et à l'intérieur maintenant de ces grands espaces-là, tu dois déterminer, trouver une manière de délimiter les conditions de l'équation polynomiale qui admettent une solution. Mais pour les délimiter, c'est pas facile. Ça revient au même problème. Voici mon ensemble, je dois décider qu'est-ce que je mets dans son ensemble et qu'est-ce que je ne mets pas. Et c'est exactement ça le problème de l'univers.
C'est des problèmes.
Pas ce que je vois directement, mais parce que tu dois avoir un moyen de décider si ce que tu mets dans cet ensemble et ce que tu mets pas. Ça démontre que c'est pas possible.
Okay, so we're on time. So yeah, please let's give a round of applause for Professor after this really and informative talk, we'll take I think on the program it's a 30 minutes break, and then so we can go out, breathe some air, and we'll come back in 30 minutes. Thank you.